Okay, let's look at a really simple example for friction to demonstrate the concepts. So here's the example we're going to look at. A 10 kilogram box is pulled along a horizontal surface by a force of 40 newtons, applied at an angle of 30 degrees. So this angle here is 30 degrees. And we're going to assume that the coefficient of kinetic friction, mu k, is 0.3. And we want to find the normal force, the friction force, the acceleration of the box, what happens if we turn the friction off, and to the acceleration. And we also want to find if the coefficient of static friction is 0.5, would the force be sufficient to get the box moving? Okay, so let's look through the list here. To find the normal force, we are going to need to sum the forces in the y direction. And if we do that, notice we would have the normal force. It's pointing up. We're going to have the component of our pulling force that's up as well. This is theta. You could think of this as FPY. So in that picture, that will be the pulling force times sine theta. And then in the negative y direction, we have the weight, force of gravity. And this will equal the mass times acceleration in y. But in this case, it's not accelerating in y, so this would become 0. So we can solve this expression for the normal force. Weight minus Fp sine theta. We can put in our numbers here. So this thing is 10 kilograms. Minus 40, 30 degrees. And we would find that this is 78 newtons. And this normal force would be in the j hat direction. Okay. So we have the normal force. What about the friction force? So to find force of friction, recognize that we have this relationship between the force of friction and the normal force. It's the friction force is the coefficient of friction times the normal force. So we have both of these ingredients, 0.3. So in this case, we're talking about kinetic friction, so we're using mu k. Just be real explicit here. So this will be 0.3 times our 78 newtons. And this would give us 23 newtons. Now notice I should have put our coordinate system in here. The force of friction is always opposing the motion, so we're pulling this thing to the right, and the force of friction will be to the left. So this would be in the negative I hat direction. Okay, so we found the force of friction. Let's find the acceleration. So to find the acceleration of the box, let's sum the forces in x. What all are we going to have? Well, there's the component of the pulling force that's in x. We have Fp cosine theta. The force of friction is to the left, so we would subtract the force of friction. And that would equal the mass times the acceleration of the box, according to Newton's second law. So if we want to find that acceleration, notice this will just be just divide through our factor of mass. Can put everything in here. 40 times cosine of 30 degrees minus our force of friction divided by the mass. And we would find that this would be about 1.1 meters per second squared. And this would be accelerating to the right, I hat. Found the acceleration when there is friction. So this is friction, kinetic friction. So what else? What happens when friction is absent? Well, this would be the same thing, except this would be the case where this friction term goes to 0. So then we would have Fp cosine theta equals the mass times the acceleration. So we would have the simpler case where this is just Fp cosine theta over m. And when we crunch that through, we would find that this is 3.5 meters per second squared. And of course, this is bigger, which makes sense. The acceleration when there isn't any friction is going to be larger than when there is friction. Find the acceleration when we have turned off the friction. And then the last question here, if the coefficient of static friction in this situation was 0.5, would the applied force be sufficient to get the box moving from rest? So what this is asking us is so let me put this in more mathematical terms. Is the pulling force greater than mu than the force of friction and static friction? And so that is Fp cosine theta greater than mu static times the normal force? So let's see. This is 0.5. Well, here, let me just write it out. So our Fp cosine theta was 35 newtons. Let me put a question mark here. Is 35 newtons greater than 0.5 times 78? And so that is 39 newtons. So 35 is not greater than 39. So this is not sufficient. It wouldn't get it moving. So in other words, the answer to this question is no. Wouldn't move. And this gets at an important point with the static friction. So the static friction is going to be exactly what it needs to match the applied force. Remember this cartoon? So in this case, our pulling force. It's going to match it. You pull harder and harder. It'll be 1 to 1. Up to a point where it would start to move. Well, it so happens in this example that our pulling force is not as large as the maximum static friction. So it isn't enough to get it over the hump to get it to move. So hopefully this simple example helps cement the ideas of the different kinds of friction and how we calculate them in a simple circumstance.